let's play with this simulator on PheT. Awesome site, PheT. I'll put a link down below. And let's use this to help us understand position, velocity, and acceleration graphs. Okay, so this is called the moving man. You can do a couple things here. You can manually change his position or velocity or acceleration, and that's fine. But I want to go up here to charts because I want to look at the graph. So click on the charts up there, and now we have a graph of the guy. Okay, or person. Let's just say person. Now, the first thing I want to do, I want to just have the person move at a constant velocity and look at the graph. Let's not worry about the acceleration graph right now. Let's just look at the velocity and time graph and the position. So I'm going to move the person way over here, and you'll see it started a graph and it moved it over there, and that's fine. I'm going to go over here to pause and clear. And now what I want to do is to set his velocity to 2 meters per second, and then I'm going to run it. Let's say for 2 seconds. 2 meters per second for 2 seconds. Let's watch the position time graph and the velocity graph. And I can click run right here, and then I'll pause it when it gets to 2, as close as 2 as possible. Oh, I went a little bit forward, that's fine. Okay, so let's just think about what these two graphs say and how they relate to each other. Number one, the relationship between the velocity and the position graph. Okay, so let's go to the board and talk about, I'll sketch these out and then we'll do some calculations in a second. So let's go to the board and look at the definition of velocity. And so this is, it doesn't matter if we're using average velocity or actual velocity, instantaneous velocity, because it doesn't change, the velocity didn't change. So we define the velocity in one dimension, the average velocity, as the change in position with respect to time. That's how we defined it. Now imagine that I have a graph of position versus time. And I start way down here at x equals negative 10 meters, right? I did that on purpose for a couple reasons. And the graph looks like this. Did it go all the way up to, no, it didn't even get all the way to 0. It looked like that. Well, what if I find the slope? That's a straight line, and I can find the slope. So the slope is defined as the change in the vertical divided by the change in the horizontal. So that's this, that, this, that. And you'll notice here, that is delta x, right? It started there, it went there, so this is x2 minus x1, that's x2, that's x1, over t2 minus t1. That's how we define slope, but oh my goodness, look at right that. That is equal to delta x over delta t. So the slope of this is the velocity. Now, if the velocity is changing, then it won't be a constant slope here. It won't be a straight line for the position time graph. And we'll see that later. But right now, let's just consider constant velocity. Now, the next thing I want to do, I want to say, well, how far did he go? How far did he go during this 2 seconds? So I have the velocity is 2 meters per second, and delta t is 2.1 seconds. I wanted to do 2, but I accidentally did 2.1. So let's just find out how far he went. That's not too hard. If I take this equation and I multiply both sides by delta t, I get delta x equals v, I'm just going to write it as v because it's not changing, times delta t. And we can calculate that. I know the velocity is 2 meters per second. The time is 2.1 seconds. Opposite is s. And you'll notice that the units cancel, and I do get 4.2 meters. 4.2. Okay. So that's the change in x. That does not tell me where he is, where the person is. It tells me the change in position. If I don't know where the person started, I don't know where they ended up. But if I know, in this case, the initial position was negative 10, so if I say x1 is negative 10 meters, then x2 is going to be, I can write delta x as x2 minus x1, so x2 is x1 plus delta x. So that's going to be equal to negative 10 plus 4.2. So you could probably do that in your head. It's not that hard, right? That's going to be 5.8 meters. So x2 is 5.8 meters. Let's check. Let's check on the thing. So switching back here. Okay, so I have here the position. If you'll see, it's kind of hard to see. It says, I'm sorry, that's negative. Negative 5.75. So, I mean, there's a rounding error going on, and that's fine. Okay, so, but you'll notice if we look over at this graph, if I look at the velocity graph, let me sketch the velocity graph. I'm going to do it back on the board. Yes, I'm going to be switching back and forth here because that's what I want to do. So here is my velocity graph, my position graph look like this. Like that. Okay. My velocity graph look like this. So that's V. This is from T1 to T2. That's delta T. So if I take, we already found the change in position was V delta T. But if I look at this V times that delta T, that's the area. So the area under a curve for velocity versus time is the displacement. It's not the position, the displacement. The slope of the position versus time graph is the velocity. Okay, now let's do a little bit more complicated motion and just see what happens. I won't do the whole thing, I just want to show it to you. Okay, so going back over here to the simulator. So I've moved for 2 seconds at a speed of 2 meters per second. What if I now have a velocity of negative 4 meters per second for 2 seconds? So I'm just going to change this. Oh, you know what? That may not work. No, for 1 second. Yeah, I can't because I can't go past negative 10. So let's do 1 meter per second for 2 seconds. So now I'm going to change this to 1 meter per second or negative 1 meter per second. I'm going to run that until it gets to 3. Oh, there. Oh, that did 1 again. Okay. So you'll see here our speed time, our position graph starts to have a negative slope right here because it has a negative velocity. And the velocity graph dips down below the axis, so you have a negative area. I can still use the area under the curve as the displacement. So let me show you what that would look like. So here, this just jumps down a little bit, like that. So if I have a negative velocity, this is going to be a negative area. So the total displacement delta x is going to be a1 plus a2, where that's the area of that, that's the area of that. This is going to be important later, but that's a negative area, okay? And you can have, if the total area is negative, that just means that the person moved backwards total displacement, okay? Slope of position versus time, velocity. Area of velocity versus time, displacement, not position. Okay, I think we're ready to look at acceleration. Let's go back and have an object move with a constant acceleration. So let's have the person back here all the way at 10. Pause it. Clear. And what I want to do is to give a constant acceleration of 2 meters per second squared for 2 seconds. I'm just picking again. So I'm going to put this at 2. And I'm going to play it for 2 seconds. I got it. Okay, 2 seconds. And I wish I could zoom in here. Huh, that's fine. You can't. So let's look at these 3 graphs and switch to the board. I'm going to draw them backwards because this is what we're going to look at first. So here's my acceleration versus time graph. And we said this was 2. I said it was 2, right? 2 for 2 seconds. So A equals 2, and that's 2 seconds. And you can even see that. So I'm going to draw it again. I was trying to save space. Okay. Right there. A, T, 2 meters per second squared, 2 seconds. You can see that one. Okay. Now, if I want to look at the velocity versus time graph, if you look at it, it looks like this. So let's go back to the definition of acceleration. So we define the acceleration as the change in velocity with respect to time. So again, we're in the same situation. If I look at velocity versus time here, I could say, here, this is v2 minus v1 over t2 minus t1. So there's v2, there's v1, and yes, slope. That is the slope. The slope of this graph is the acceleration. But you'll notice that the velocity is increasing, which is exactly what that says, right? That's what the acceleration says. What about this? What does the area under this graph tell us? Well, if I go over here and solve for delta v, I get delta v is a delta t, but this is delta t, and that's a. And if I multiply delta t by a, I get the area. So the area is equal to the change in velocity. Again, it doesn't tell you the velocity, the final velocity. It tells us the change in velocity. If you don't know that it started from rest or what speed it started from, you can't calculate that. So the area of an acceleration versus time graph is the change in velocity. The slope of a velocity graph is the acceleration. But we said before, the area under the velocity graph was the change in position. But here, I have a triangle. So what's the area of a triangle? Well, that's 1/2 base times height. So here the base is delta t. There's the height is v final, right? So it's going to be 1/2 times v2. Well, this is v1. Let's call this v1 to v2. The height is going to be v2 minus v1 times delta t. So that is the displacement. Even though it's not constant, that's fine. You can still find the area under the curve. And that's still the displacement. In this case, it would be positive. Now, think about this. If let's just multiply this whole thing out. So let's say delta x is 1/2 v, 1/2, I'm going to say, let's say it right, 1/2 v2 delta t minus 1/2 v1 delta t. And then if I find the final velocity from the acceleration up here, I can say v2 equals v1 plus a delta t. That's delta. I'm thinking ahead. That's what I'm doing. So this is v2 minus v1. Add v1 to both sides to get that. Now if I put that in down here, I get delta x is 1/2 v2, which is going to be v1 plus a delta t times delta t minus 1/2 v1 delta t. And if you multiply everything out, you know what you get? And you should do this on your own. I've already done it in another video. I get this. Delta x is v1 delta t plus 1/2 a delta t squared. That is the kinematic equation. If we let x equal x0 at t equals 0 and t1 is 0, I get x minus x0 v1t, they call it v0, plus 1/2 a t squared. There's your kinematic equation. And if you go and look at the what that graph looks like, this says x is proportional to t squared. That's a parabola. And you'll look over here, we do indeed have, oh, we started down here. a parabola, and this is x versus t. Now, let's just check one more time, right? This says that the slope of the position versus time graph is the velocity. Well, what's the slope of this graph right down here? 0. What's the velocity? 0. What's the slope of the graph right here? Well, now some positive number greater than 0, the velocity increased. What's the slope up here? What's even greater? The velocity increased. So this is a non-constant velocity, and the slope is not constant, but it agrees with the graph above it. Okay. Area under the acceleration versus time graph is the change in velocity. Slope of the velocity versus time graph is the acceleration. Area under the velocity versus time graph is the position. Slope of the position versus time graph is the velocity. And that's what you need to know about position graphs or motion graphs. And it does get a little confusing. Play with the Moving Man simulator. It can help. You do have to run it in, it's an HTML5. It's not HTML5. There's like an emulator for it. So, but I'll put a link for that.